Hello, my name is Leandro and this is Reasonable Coding. It's a live stream of reasonable software engineering or development, whatever you feel more comfortable calling it. In today's episode, we'll be talking a little bit about LWT, which is an asynchronous computation library that we'll be using for, doing asynchronous things. Normally in other languages that support asynchrony at the runtime level, such as Erlang or perhaps JavaScript with their promises. You'd not need to rely on a third-party library to work with these things, but in OCaml, this isn't supported by itself, so it had to be built at some point. I don't know much about this library. I've used for a bunch of projects. I can understand the whole concept of an event loop and what is a promise and what not. But I really wanted to dig into how things work inside. So we'll start from the beginning. We'll begin at the high-level documentation, and we'll start digging deeper and trying to understand what it is. Not just what it is, but also how it works, right? So in this in-depth episode, we don't necessarily expect to build anything cool. Rather just have a much better understanding of what is the code really doing. We may also build some small things on the way. We'll see. It might be that for some of these things, it's for some of these concepts, it's better to build a little program to understand, oh, this is what this is doing, and so on. And if we need to do that, we will be using Reason as a syntax and Dune as the build system. Unfortunately, I could not finish my Twitch board. It's a CLI application tool for getting statistics of the Twitch stream, such as the amount of currently viewing users and the chats, which I'm also building in some of these live streams, in some of the past actually. So I'll have to go back and forth my phone, which means I will probably miss some of your comments every now and then. If you make some. Okay, so first things first, I'm gonna close Twitter and other personal things. I should have done this before. That's fine. By the way, how do you like the new brand thing, logo? This is perhaps a teaser of some of the things that I have in mind in the future. I know that I've been mostly talking about Reason, but I've done plenty of Erlang development professionally, and I would really like to get back into it. And at work, I do a lot of Java, and I think that there's a bunch of languages in this list that I would like to maybe not necessarily contrast, but at some point maybe just build something interesting with them, right? For example, some of the live streams that I have planned in the future is to build a GraphQL server like the one that we built with OCaml GraphQL server in Erlang to see what are the trade-offs, right? We have this strongly statically typed language, Reason or OCaml, and then we have this strongly but dynamically typed language like Erlang. And we want to build the same thing. Which one makes it easier? Which one makes it more safer? Which one makes it faster? And so on. There's going to be trade-offs here, and whereas perhaps Reason or OCaml native give you the best performance on a single core, Erlang gives you better performance as you scale out through the SMP feature of the Beam, which is the runtime. SMP stands for symmetric multiprocessing, which roughly translates to your program will run in as many cores as you throw it, which is a nice property of Erlang programs and the actor model in general. Okay. Now let's give it a moment and see if anyone is responding on any of the channels, and then I'll get started. All right. I think I'll just start by looking at the docs, right? Oops, I had it open over there. Okay, so if you land on this page, this will just take you to the live stream, so you can just use that. Anyways, let's begin. Synchronous programming with promises. We know that already. Promise a placeholder for a single value, which might take a long time to compute. Speaking roughly, a promise is a ref. So this can be filled in later. We've been through this before. So promises are optional, write one references. Right, but this is going to give me the understanding of how to use it, like higher level flows, and essentially what the APIs for handling these promises is going to look like. What I really want to know is how this is being executed underneath. So I guess I'm going to assume that if you're watching this, you also have an idea of what a promise is from JavaScript at least, or any other language that has monadic I/O of some sort. Perhaps a future from Haskell or Scala, or a completed future from, or completion stage from Java as well. Okay, if that's the case, then you can just go through some of these. You have some combinators here to create some promises. Some of them are part of the I/O library that has essentially ways of doing input and output, and then the Unix module, which is a lower level version of the same thing. I mean, they're not really a one-to-one mapping, right? But and you build a promise by essentially resolve. How do you build a promise from scratch? Like I've seen a lot of functions that return them that come from the library, but where is it that we can define a promise from zero, right? Okay, you know what? Let's read about the execution model and what is it? Quick sort. Execution model. Great. That link doesn't work. Okay, let's go down a little bit and we'll get there. It's important to understand promises are pure OCaml data type. They don't do anything fancy, right? They just are data. Listal callbacks, if pending, or containers for one value. Alright. The interesting function is LWT main run. It's wrapped around select equal, right. Right, okay, so I guess that all of the functions that we're going to be using are just going to be manipulating some data, and the data will describe what we want to do. And then at some point, LWT main run will take this one giant promise and do something with it. So let's figure out what is it that really happens with that. Okay, so there has to be some mapping between the I/O that's supposed to finish and the promise that needs to be resolved somewhere. I'm actually gonna take some notes. So if I open, what is it? Yay, what is all that? So promises are data. There's a mapping between a promise and some underlying IO that will be executed. Terminal width 80. The event loop, actually I haven't read the words event loop just yet. Well, I'm going to close this because we're not going to be showing it anytime soon. Okay, the main IO loop will yield the program, and once a certain IO operation finishes, it will look into the mapping and resolve the appropriate promise. Note, the mapping may not be a table. It may just be a function reference. I'm not sure how this is working inside, but whatever, let's move on. We can fill the gaps as we go on. So resolving is an ordinary OCaml operation. It causes all the callbacks of L1 promise to run, one after another. Each callback is also ordinary OCaml code. In our case, there's only one callback, but in general, there might be several, and they might also resolve additional promises. So promise resolution triggers a cascade of callbacks, right? Eventually, however, we should run out of callbacks and control will return to right. I wonder if you have a promise, right? Let's say A. Then when you say LWT main run, then this promise A will let's say it has a promise B attached to it. Well, sorry, what I meant is if it has a callback F and another one G and another one H, then when the underlying mechanism resolves A to, let's say, 1, then it will call F1 and then call G1 and then call H1. Actually, so this happens first and then it returns control. Return to LWT main, the run, which is interesting. I don't really know how this is precisely or actually implemented in the code, so that's what I want to find out. I want to get out of here with an understanding of exactly how this works internally. I want to be able to make an LWT light, right? Or like a crap promise, or like a pinky promise, if you will, a library super tiny that does the same thing, roughly, maybe without any of the magic operations that magic operators or all the libraries built around LWT, but that essentially lets me know that not only I understand what this concurrent construct is, but also, or how to use this concurrent construct, but also how to implement it if I need to. And in particular, I think this will be very interesting to keep in mind and close for trying to build runtimes for other systems. Like if you wanted to build a layer on top of this, then you have an engine, right? A runtime that can run concurrent computations. So then if you abstract this in your, let's say, little language on top of it, then your little language could include these concurrent computations as part of its syntax and so on. Which would be interesting, kind of like Go routines. So going back. One sec, I'm adjusting the microphone. Because I've got a microphone now. There we go. So, in our example over here, right, our one callback registers the second IO. So the magic might actually happen in some of these methods that talked through LWT main to register some of the actual underlying IO operations, so that it knows that when that particular operation finishes, then in this case this function, right, should be executed, since we're binding this function to the resolution of this promise. Then there are no callbacks left to run after that, so control returns to main. So far that makes sense to me. Hopefully that makes sense to you too. And main goes back to sleep again by calling select2. Now I understand select2 is an underlying asynchronous IO API. I do not know where it comes from. I'm gonna assume it's something from Unix, and it's Linux. Okay, synchronous. Let's look at this one. Let's see what it says. According to POSIX 1/2001 or synopsis, select and pselect allow a program to monitor multiple file descriptors, waiting until one or more of the file descriptors become ready for some class of IO operation. Input possible. A file descriptor is considered ready if it's possible to perform a corresponding IO operation, like reading or writing. Okay, that makes sense. So essentially, since all operations really happen in a Unix system through a file system, then you can say, okay, I want to be notified whenever some file, right, which could be a socket, could be an actual file. By an actual file, I mean something that a human would open, I guess. I might be wrong. And then if at some point you can read or write to it, then it will ping you. Yeah, okay. So this has two major implications, a good and a bad one. They have, okay, let's begin with a bad one. If one of your callbacks enters an infinite loop, calls an LWT unfriendly blocking IO, or just runs for a real long time, it won't return control to LWT main run anytime soon. That means won't get a chance to resolve any other promises. Okay. In case your callback is just in the CPU for a long time, you can insert a few callback calls to yield into it and resume your computation in callbacks of yield. But this is the same as Unix sleep. It's a promise that will be resolved by... Right. Oh, okay. So if you're... some computation is very long or intensive, you can just put a few yields in the middle so that essentially after everything else is done, then it can run. I wonder if you could, or if it makes sense to at some point insert yields between several of the steps of your function, just to be able to more granularly task switch or switch tasks. I guess it will depend on how you're building your application and what your constraints are. The good implication is that all your callbacks run in a single thread. This means that in most situations you don't have to worry about locks, synchronization, etc. Anything that is in the same callback is guaranteed to run without interruption. LWT programs are often much easier to write and refactor than equivalent programs written with threads, but both are concurrent. This module LWT is the pure OCaml definition of promises and callback calling. It has a few extras on top of what's described above, like rejection. Interesting. There is nothing conceptually special about rejection. It's just that you can ask for callbacks to run only on fulfillment, only on rejection, etc. Okay. Cancellation. Okay. Concurrency helpers. All of this could be implemented on top of LWT bind, as we saw. LWT concurrency requires only deciding whether to run something inside a callback or outside it, and these functions just implement common patterns and make intent explicit. And then there's a few helpers and deprecated APIs. So, okay. Interesting. Okay. So slowly building up an idea of what this is about. I'm gonna get some napkins. Back. So a result promise is one that is either fulfilled or rejected, i.e. not pending. Once a promise is resolved, its contents cannot change. Okay, let's begin at that. What the hell is that class A? Type Right. Okay. That makes sense. Sorry, I just read something in a different link. Often seen plus A or minus A. I think it's variance and covariance and contravariance, maybe. What does plus in front of the generic parameter do? From a little experiment, I am able to discern the difference if plus minus is removed from the type declarations. From the manual page, okay. And this is a nice blog post from Jane Street. Damn it. The type variables appearing as type parameters can optionally be prefixed by plus or minus to indicate that the type constructor is covariant or contravariant with respect to its parameter, to this parameter. This variance information is used to decide subtype relations when checking the validity of, I don't know how to read this, bigger than coercions. For instance, type plus A, T declares T as an abstract type that is covariant in its parameter. This means that if the type T is a subtype of the type tau and rho, then tau, is that tau? Yeah, tough. And this is sigma, this is not rho. Then tau T is a subtype of sigma T. Similarly, type minus A declares that the abstract type is contravariant in its parameter. If tau is a subtype of sigma, then the other way around. Okay. If no plus or minus invariance annotation is given, the type constructor is assumed non-variant in the corresponding parameter. For instance, the abstract type declaration type T means that tau T is neither a subtype nor a supertype of sigma T if tau is subtype of sigma. Okay. So I guess that there is a relation between the two different types, or more than one type that we're going to be making use of. Uh-huh. Interesting. Right, so the variance is specified here. Okay, so I get the gist of what this is going to be used for. Let's take a look at this one last blog post from Jane Street. Should be a 5-minute read, and then we'll try to figure out why. I mean, I guess we will find at some point why we need this in LWT. If you ever wonder what it means in OCaml when there is front of a type variable redone, OCaml has subtyping, which is a binary relation of types that says roughly if type T1 is a subtype of type T2, then any value of type T1 can be used anywhere a value of type T2 was expected. In OCaml, subtyping arises from polymorphic variance. Okay. Right. For example, A is subtype of AB. So I can tell this is an X. This X is of type A. I mean, how do you read this? Polymorphic variant with constructor A, but it should really be one of these. But the one on the right should always be bigger than the one on the left. Right. Right. I'm going to leave this too as a reference for later. And I'm going to go back to the docs from Oxygen. So roughly, right, we will have some type that will be covariant on its parameter, which means we can make Will you believe me if I told you that I thought I understood it, but I can't remember what exactly meant? We can give it tighter inputs, essentially. Yeah, we can give it subtypes of this type, but we cannot give it types. This is our type is a subtype of. That's why I understood. If you have a better idea of what this means, then do let me know. So our result promises one is we read this before. Promises are write once references. The only possible state changes are 1 from pending to fulfilled and 2 from pending to rejected. Promises are typically read by attaching callbacks to them. The most basic functions for that are LODT bind, which attaches a callback that is called when a promise becomes fulfilled, and LODT catch for rejection. Promise variables of this type. Separate resolvers of type U, this one, which are contravariant, are used to write to them. Right, and this kind of makes sense because when you resolve, this would be the input, and this would be the output. And as we saw over here, the arrow type, right, essentially has the input as a contravariant and the output as variant. Right, for tuple arrow types, yes. The arrow type constructor is contravariant in its first argument and covariant in its second. I will need to read some of that later to make sure I understand what exactly means that. What exactly that means. Each resolver can be thought of as the right end of one promise, right? It can be passed to wake up later exception, or wake up later result to resolve the promise. So task is a thing that creates a promise with a resolver. So task is our fundamental promise constructor. And then we see some of the functions that we can use to work with promises. Binding is what puts callbacks in it. Okay. Alright. Let's go straight into main. I remember seeing somewhere in one of these modules something saying that excruciating or painful amount of detail. Yeah. Here. After that is the reference proper, which goes into painful levels of detail in every single type and value in this module. Please be safe and read only what you need from it. But I don't think this reference proper actually takes me to a different place. This is the same place. So I have an idea, and I think that maybe we want to take a look at the source in GitHub. Or dev, I guess. Is there anything different here? This looks a little different. Yeah. Okay. What did I see? Oh, okay. So wait is not really cancelable, but task is. Okay, I was a little confused about why they introduced wait somewhere on here. Right? But as it turns out, it appears that wait is not a cancelable promise, it's just rejectable or fulfillable. We can also switch to the reason syntax. Anyways, let's go to GitHub. Oxygen, where is it? LWT, no. Alright, there we go. Cool. Somewhere in core, we have the main interface for the whole thing. And this is, well, I guess this is not for the faint-hearted, is how you say it? A promise is a placeholder for single value which takes a long time to compute. Speaking roughly, a promise is a ref that can be filled in later. To make that precise, here's a promise different from refs. Okay, we've seen this. We've gone through all this. Right, so I guess what's left here is to start digging into the actual implementation of some of these things. So far we know that a promise is a piece of data that whenever we call one of the LWT IO or LWT Unix calls, there will be essentially a data structure describing what IO operation LWT main needs to execute. So if this one was LWT IO, read file, I think read there. And we have all of these promises there. I'm just gonna duplicate that twice and say that. There you go. Then this call will register this particular underlying IO operation, and it will spawn a new process, if I understand this correctly. It might be wrong, so we'll verify it in a minute. And okay, so essentially if we write this down, we'll be like 1, LWT main executes the related IO to the LWT IO to read their promise, which would be spawn a process that will run read there. I guess we can say ls for the sake of this example. And it will link the promise to that process, returning a value. So when the process finishes, returning a value, and this okay, we'll do a promise sleeps. LWT main sleeps until the process is finished, and then resolves the promise. I'm gonna write out the whole thing. Promise with the return value. So LWT read there will call then all of its subscribers. Which may go back to number 1. Eventually, control flow returns to LWT main.run, and the program, the event loop, finishes. Alright, so this is my understanding of what's going on right now. It doesn't mean it's right. It's just what I understand right now. And I'm really wondering what the hell, how is it implemented? I'm gonna leave a comment here, type T and then type minus B U, and this is type of the promise, and this is type of the resolver. And if you think about it, since the type of a function is type E contravariant A, and okay, I'm gonna do the same letters as above so it's not confusing. F, and then you get like B, F, oops, A. Then you can see that the promise will result in this type, but the resolver has to bring one of this. So that's confusing me so much right now. Does this mean that when you call a resolver, you need to give it a type that is lesser than, and then when you resolve the promise, or the promise resolves, you get a type that is not lesser than, but instead is bigger than? I am confused. MailChimp, what's new? Okay. All right. So now we can look into the implementation. No, you know what? I want to understand this. I hate not understanding what the hell exactly does that little plus and minus means over there. J-Rox, hey, I think someone actually... Welcome, by the way. I think someone actually tried to do something like this before. I think I remember Beam F sharp. FES, F sharp to core Erlang compiler experiment. Which, I mean, it's not precisely OCaml, but it's an ML type language and it's similar. So it has functional modules, functions, operators, pattern matching and flow control is complete. Nice. Yeah, it has a bunch of things here, as you can see. The rest is mostly erased as all I/O is already non-blocking in Erlang. Interesting. Cool. Have a look at this if you feel like it. Might be a good idea to try it out. Cool. Okay, so going back. So I was going to essentially spend some more time with this thing. Gotta love Jane Street's branding. I mean, they really want to sell, the brand like FP meets the real world. This is where we do cool shit with functional programming. So many ads. Maybe I should try applying. I don't know. I don't think I know enough of OCaml for their level. Anyways, OCaml has subtyping, which is the binary relation, right? So roughly says that the type 1 is a subtype of type 2. Okay, so this will be used for polymorphic variance, and it works also for, if I understood, for polymorphic variance both on ends of a function, but also on tuples. So this tuple here is essentially strictly smaller than this tuple over here, right? If you look at the inputs, then this one has an A and a B, and that, I mean, inputs to this coercion operation, right? And then this is being coerced into a bigger type. So we can take a look at this and try it. And for those purposes, I think I'm gonna just, I do not know if we can just throw in a module definition here in UTOP. Yeah, we can. Cool. So we can copy this and put it there, and kind of makes sense. You define a function f with an input x, and we say this will just return x, but given that the type is this one, right, we're gonna try to coerce it into this other thing here. So if we run this, it says there's a syntax error. What the hell? Oh, right. Ugh, sorry. All of these need backticks. The reason they don't have them is that there was a problem with the rendering in the blog post. That I can remember, but I can't remember what the plus and minus is. Come on. It's somewhere here. Typographical note, in this post, polymorphic variants are written without the leading grave accent. How do you pronounce this? Grave. Okay. Cool. Where's the module that we were looking at? Here. Okay. So if we do that and we run it, then of course, this thing is not a subtype of that other thing over there. And it says the first variant type does not allow tags s. So now the question that they pose is, if we change the signature of this module, right? If we make a module and prime that will have a signature, right? And the signature will essentially have a type that will be polymorphic, will be covariant over the first type and not over the second, just for kicks. Let's try that, right? Then we can define this module and we can say that the type A and B of T equals product of types. What did I just say? I said that there's a type. Where is my tilde? There you go. Right. So the constructor will be the tuple. Okay, this should be fine, I believe. And we run that, and we get our m prime that has our alpha plus alpha, or covariant alpha type parameter for our type T. So that means if we do left f, x, and then we say x could be an A, right, and a B of m prime T, right? But we're gonna, okay, if we do this, this should run, perfect, it works. Now if we do f prime and we try to coerce this, I guess this will be a more general type. Huh. So I wonder how would that look, like if we have to make an analogy or a comparison with subclassing in a different language, subtyping, not subclassing necessarily. I don't know. I think I'm in over my head when I say subclassing and I try to connect it to subtyping. There might be a relation there. I'm not sure what it is. I think I need to recur to some more Benjamin Pierce material to be able to understand better. Anyways, we have an A and we should be able to also throw in a C, right? But we should not be able to throw in anything other than B here. So let's see if the m prime T works. And if this works, then we can try out with something more. And that works perfectly. So that means that when you have a plus, right, you're allowing, where is it here? You're allowing your type to be casted to bigger types. But if we do D here, this should fail. Brilliant. Nice, this is interesting. I wonder if in HTTP-Kit I can make some changes to the interfaces to constrain some of these things, because I already am using a lot of type state in this library to be able to determine whether the server is clean, is currently listening, or has middleware, right? On whether it has or not responded. So essentially, when you build a new server, you have a clean one without a response, and then as soon as you put a middleware through it, then it says it has middleware, and then as soon as you respond, it will return you essentially a server that has responded, and of course responding acts as a middleware. So if you have a clean server, then it becomes a server with a middleware. But then the part that does the actual listening in the transports, right? What? Where's the transports? Listen. Right. This thing requires a server that has middleware and has already responded, which means you can only start listening on a server that has called the other two functions, which is very, very handy, because you can build something like a hello world like this, where if I take these two things out, then I actually get a type error saying, hey, you wanted something with middleware and responded, but instead you gave me a clean server with no response. Even if I use a middleware in the middle, it will still tell me, hey, this one has middleware but hasn't responded. What the hell? So I wonder if there's something that we could use in the definition of this this type. So for example, minus would mean that you can always go into a subtype of this status, right? But you can never go into a bigger one. So you can go from clean or listening or middleware to listening or middleware, or to just listen. It might make sense to have the state in be contravariant and the state out be covariant, so that you can always send a state that is smaller than expected and get a state that is bigger than expected. I don't know. Let's continue experimenting and we'll get that out of the way. Oh, so that's it. What? Is that all? Okay. So if we throw a plus, then whatever type you give something, or it has, you can turn it into a bigger type. If you give it a minus, you can turn it into a smaller type. Let's try out the smaller type with a module and prime, which will have a type, and this would be plus a. Let's do plus a and minus b, right? And then t and struct, and then type, and then a, and then b, t. It should be equals to a, and then we can do products. Yay! Cool. What did it do? How is this different from what we had before? Did I use? No. So before, if we look at this, right? So confused. And the error is that signature mismatch, modules do not match. Uh-huh. Interesting. So they have plus plus for the type and then plus plus for there, but minus. What an obscure language feature. Useful indeed, but fairly obscure. Okay, so for the product we can use one, and I guess we can also use the other. Like if I go, if I go up there, I'll be able to say that this will hold as well, and that works. Huh. Let's change letter. Sake, and then type, and then we have what happens if we do just minus b? Why doesn't this work? And struct, and then type. All right. So it appears that the covariance, the contravariance does not agree with the constructor here. So I wonder if we change this to be something else, to be like hello AB, right? We have an error. Oh, my bad. This should be, oops. Sorry, too much reason. No. Okay, that makes sense. Sorry, we will still need to have the product there, so kind of stupid not to have seen that before. Yikes. Sorry. So we can't seem to put any of this as contravariant. They can only be covariant. I wonder why. But we can put both of them as covariant. And then we can always take a tuple and make it a bigger tuple, a tuple of bigger types. But for function, interestingly, I expect this one to. I would have expected this one to work. I need to sort of understand why. And okay, I think if you define, okay, so it sort of makes sense that if you define a function, right, for, let's say, if you define f, right, to work on, that's a function, on some type A, and this would be 1, oops, and some constructor B, right, this would be 2, then this function works on those things, which means it can take at most these two. It can take less than these two things. So you can call f with A or f with B, and that should work. However, we should be able to constrain this function to be a function that goes from just A, right, to int. I guess we need a. And that works. So that means if I try to call that function with B, then I should get a type error. Okay, so now that makes sense. Why? Because the type of a function, oops, if I don't know if that's an operator. No, okay. I figured that might have been an operator. But the type of a function will be, as we saw here, right, will be contravariant over its input. You can always send an input of a smaller type, but you can never give it an input of a bigger type. Why? Because if I take this function and I say, oh, well, you know what, this function works on A and B and also C, then the body of this function, which we saw here, right, doesn't handle C. This will fail. So naturally it can be that. However, for the outputs, it's perfectly fine for it to return something else. So we can do another experiment. We can say g is a function, right? And for A, it will return z, and for B, it will return y. It's kind of a reverse alphabetical thing. And there, and then we can see already that for inputs it can take no more than these two, and for outputs it can take. It will output at least one of these two. So you can take G and say, you know what, I actually need G to be from A and B to be a function of Y and Z, but also X. And this should work fine. Why? Because we will always be able to handle all of the inputs, we would just never produce all of the outputs. And that's fine. Boom. So of A works and of B works. And since we can give it an input that would produce X, it's just perfectly safe to keep adding some output types to this thing. Okay, so I have learned something new, which is very nice. It's not directly related to promises, but it's certainly directed to how the promises are being typed internally, and that's what we want to take a look at. So now we know why on earth this promise type has this plus and minuses there, and it's a very nice thing to know. It feels like this sort of obscure thing in the language, especially because OCaml sometimes has its way of having, you know, backticks and tildes and pluses and minuses and brackets and all the other symbols everywhere, and that you're not familiar with if you come from an Algol or C style language. But clearly it's useful for some things. Like if we have a function, another function that requires inputs x, y, z, right? Let's say h, and this actually needs function x, and this will be 1, and then y 2, and then z 3. Then calling, a, and then g, and then h. Alright, it's not gonna work. What? It works? Oh my god, I am full of shit. But why? Right, because you're giving it. Okay, you're giving it less than this, and this already is less than this. Huh. I'm starting to question the utility of this, because my first example didn't work, but that could just mean that I haven't understood it completely, or rather understood why it's useful. So let's look into a library that actually seems to be make using of this to understand why it's useful. Where's the code? That's fast. Wait, I want to see the variance here. Somewhere here. Okay. Cool. Hey Shikara. No, I'm actually right now. I'm just running natively using Reason with the OCaml toolchain. So we're not writing any code right now. We're just looking into a library, trying to understand how LWT, the concurrent programming library, LWT works internally, what types he has, and why he has those types, and how does he handle everything. I'll post some of these notes afterwards. Like essentially, promises are just data, and there's a mapping between a promise and some underlying IO, and need to figure out where the mapping is, and so on. I guess at some point I read what the promise type was like, and it looked super weird with this plus and minus, so I started looking into what the hell are those, and then we got around understanding first what those are before we continue into the actual implementation. So thank you, I just understood what exactly was I doing before we got distracted with the plus and minus again, the variance and the covariance of the parameter of the types. So let's go back to the implementation of LWT. Somewhere in here we have type plus a LWT, just t, and this is the interface. So if I go into the ML file, maybe I'll find something else. Reading guide. Welcome to the implementation of the LWT core. This is the big file, but we hope that reading it parts of the time will not be scary. Here's why. Sectioning. The code is broken up into sections, each one of which is an internal module. Most of the modules have a signature, which serves as a neat table of contents. It is recommended that you read this file with code folding enabled. If you fold all the modules, you can visualize the logical structure of LWT quite easily. You can then expand modules as needed, depending on what part of the implementation you're interested in. Yes, yeah, okay, that makes sense. You can still visually parse the file, however, because there are plenty of blank lines that say the help section things off. Because there are plenty of blank lines to help section things off. Okay, right. Oh, thank you so much, Antron, for folding this thing for us. Let's take a look at what this looks like. Reading guide overview. Wow, this thing is really well organized. Huh. Interesting. Big comments are absent. They're moved into the modules. Okay, there we go. Overview. In this file, there is a model function, LWT bind, which pulls together many, though not all, of the concepts and helpers discussed in this overview. To find it, search for let bind. Makes sense. You can examine it while reading the overview. The authors of this file intended to put extra effort into writing nice comments inside LWT bind. Thank you, authors of this document. Honestly, I'm already really digging not only the amount of comments, but also the tone they have. They clearly want to make this amenable for reading. I keep saying amenable. Maybe it doesn't mean what I think it means. Open and responsive to suggestion, easily persuaded, docile, complacent, pliant, responsive, tract. Huh. Yeah, maybe it doesn't mean what I think it means. Complacent. Yeah, cooperative. Okay, I guess one one synonym away, the meaning makes more sense. And we also have amenable groups in mathematics. Huh. All right. Going back to that. Main mechanisms and two aspects. The LWT interface provides one main mechanism, promises, and two aspects, which are not necessary to understand the main mechanism promises, but they are still there. Promise cancellation and sequence associated storage. What? If you're not interested in cancellation or storage, you can ignore these two complications and still get a pretty good understanding of the code. To help, all identifiers related to cancellation contain the string cancel. And all identifiers related to storage contain storage. Alright, so what is a promise? A promise is a cell that can be in two states, result or pending. Result promises are either fulfilled with a value, rejected with an exception. The state of a result promise will never change again. A result promise is basically equivalent to a result. Result promises are produced in two ways. Yikes. Return or fail and related functions produce trivial promises that are resolved from the start. The other way is to resolve a promise that started out pending. Okay. Note that rejected promises have nothing to do with unhandled exceptions. And then we have pending promises, which are those that may become resolved in the future. Each pending promise carries a list of callbacks. These callbacks are added by functions like bind and called by LWT when the promise is resolved. Okay, so far my intuition of what a promise is, let's say there's a picket promise reason file here, and we will have our type, which will be a promise t parameterized by some value, which should always be bigger than, should allow to be casted to something bigger than it really is. And this can either be a pending promise, right? That has a list of callbacks. Yes. Or it could be a resolve promise, which has either a result of type A or some error. And the error can be, I don't know, exception. Is exception valid type identifier? I think it's EXN. Right, cool. So that's so far what I understand, right? And then when you create a promise, you have something like make that, let's say task, right? That essentially creates a promise by saying like pending, and then this is the list of callbacks, right? Empty list of callbacks, and then it returns you two functions from what we saw. One function is for resolving it. So this is like a ref, really. And another function is for canceling. So like resolve is a function that when you call it with some value, so x, it will mutate the promise. I guess first it will get the callbacks out, so it will be like let actually like a switch promise, and if you get a pending, then of course you can callbacks, and then you can just list it either, I don't know, like callbacks with x, and then if you have resolved, then you do nothing. But you probably here want to mutate it and say promise will be now a result promise with a result with an OK of x, something like this, right? This doesn't need to. It's not aiming to be a proper implementation of promises. Alright, so just so that the formatting doesn't go bananas like it's doing right now, we can do callbacks, and then this will be something like a list.iter, and then you have a callback, and then you call the callback with that. For example, I don't disclaimer. I don't think this is the actual implementation, but it will be something like that. So we need to return that resolve, but also we need to return. I'm going to call this make, but also we need to return we need to return the promise itself. So now if we call make, right, then we have a promise. So let the promise and then resolve. So ideally we'll be able to call something like then, and then this will be a function that will run afterwards, right? And this would maybe do just x plus 1, right? And then at some point we can just call res with 1, and then this function should be executed, should be called. How or why? Because this function res, which is resolve, actually has in its scope the promise reference, so it can modify it, and it knows exactly how many promises are there. This then function here, which we did not define anywhere, will look a little bit like this. I believe this might not be the right thing to do, but this will be a function, this will be a promise, right? So if the promise is resolved, I don't know, let's just assume the promise isn't right now. So if we get the value out of the promise, which of course it's opaque to the user of this library. If we get the value out, then if it's pending, then we will get a list of callbacks, right? And we'll just return pending, and we will add f to the list of callbacks. Well, not quite add, but rather take this and modify it, mutate it. And if it's resolved, then we get some result here, and then we can just call f with the results or something like this. And then we just return the promise, so you can change this chain this thing together. which means I'm having trouble typing some of these things, but I think it's because I'm not building anything. But essentially, you'll be able to change this thing and just thread a promise through a bunch of dents that will modify the promise reference and so on. I think it will look something like this. This is just my intuition. Of course, this doesn't have any runtime for it yet. Everything that you do executes sort of synchronously, right? I mean, you do then, you chain all these callbacks, which is essentially just building a list of whatever the callback type is, right? And then eventually you run them. When you resolve them, all of the functions execute one after the other, which really is just it's really just a monadic composition. Not much to see there. Okay, let's return back to the code and see what we can learn. So pending promises are produced in 3 ways according to how they can be resolved. Initial promises with wait or task. You need to handle those with your own. Sequential composition is with bind. Which is a promise that kind of mixes two things together, like puts one function after the other. I think this bind would be our then. No, actually this would be map. The user cannot resolve these promises directly, but see the section on cancellation below. Concurrent composition, for example, LBT join or choose. These promises are only resolved when all or one of a set of preceding promises resolved. The user cannot resolve these promises directly, but see the section on cancellation below. Okay. Resolvers. Resolvers are given to the user by wait and task, and can be used by the user to resolve the corresponding promises. Note that this means that the user only ever gets resolvers for initial promises. What's interesting here is that most of the promises that you normally use when working with LWT never expose that resolver for you because they're handling it for you. So it's a very nice pattern, really. It hides the fact that that's even a promise. You just say LWT IO, read file, and then you don't have to do anything about it. It does its own thing underneath, and then eventually the thing that you're sequencing after it will be evaluated. JRox, which line? Could you point me to one of the lines? 9 and 12. 9 and 12. Well, so pending should have a list of callbacks, and you want to, when you're resolving it, if the thing is pending, then you want to call the functions for the first time and then put this thing to be resolved. And when it's resolved, then you don't want to do anything because it's already resolved, right? So I think it's right. I think that if you have a promise that's already resolved, then resolving it again doesn't really work. It does nothing. Does that make sense? No worries. That's literally what we're doing here, right? Trying to understand how the shit does this work. Right, so internally resolvers are exact same objects as the promises they resolve. Weird. even though the resolver is exposed as a reference of a different type. For details on why, see section type system abuse below. Oh, I want to read this now. I really do. That must be so exciting. Callbacks are attached by LWT to pending promises and are run by LWT. Right. So the callbacks are attached to pending promises, which means in the code, like the crappy pinky promise implementation we have here, when you resolve, you take all of the callbacks and run them, but when you then you essentially are adding a new callback to this thing. And line 21 should be spread, I think. Okay. So these callbacks are not directly exposed through the interface. They are a low-level mechanism. For example, to implement bindpf, LWT attaches a callback to P that does some internal LWT bookkeeping, and then calls F if P is fulfilled, and does something else if P is rejected. What? Okay. That sort of makes sense, right? If you want to join two things, and the two things don't know about each other, then you may need to put something in the middle that understands one and understands the other and can thread things around. So callbacks come in two flavors. Regular callbacks and cancel callbacks. The only material differences between them are that regular callbacks are always called when a promise is resolved, but cancel callbacks are called, in addition, only if the promise is cancelled. And all cancelled callbacks of a promise are called before any regular callback is called. Okay, this seems to be a special case of resolution, a particular special case of rejection. I'm going to skip the cancellation part. I want to get something up and running that sort of resolves things, and then we can see how we can cancellate or reject things. Resolution loop. Interesting. All right. Resolving a pending promise triggers its callbacks. Those might resolve more pending promises, triggering more callbacks. Okay, now that starts to make sense, right? So from this little bit here, we already know that what we have here kind of makes sense. When you resolve a pending promise, then you have to execute all the callbacks and mark the promise as resolved. And I think I might know what they're doing with this plus and minus. My intuition tells me that maybe they're using it to constrain phantom types that they'll use to prevent the promise from being resolved more than once. But never mind that side comment. Essentially, calling resolve on a pending promise will execute all of the callbacks with value. Trigger its callbacks. And if those callbacks have callbacks and so on and so forth, it just continues. This behavior is the resolution loop. LWT has some machinery to avoid stack overflow and other unfortunate situations during this loop. It would be interesting to know what kind of machinery it has. This chaining of promises, resolutions. Sorry. Yawning already. It's getting late over here. Don't worry, until we don't crack this thing, we're not going to stop. This chaining of promise resolutions through callbacks can be seen as a kind of promise dependency graph. Yeah, that makes sense. Like if you were to structure this thing, right, as a dependency graph, then it would make sense that when you resolve a parent, then you have to try to resolve all of its children. And then each one of these children may actually have multiple callbacks which are children as well, and so on. By the way, if you're liking any of this and you enjoy either the way I read things out loud, my beautiful boys, pronunciation problem with Spanish speakers. B and B sound the same to me, so I need to pay a lot of attention to it. But if you're liking any of it, not only I'll suggest do follow me on Twitch. There's an events section over here that you can go into and see, hey, what's gonna be happening sometime in the future, but also what's happened in the past, and you can check some videos. Now the cool part is that there's a cool part to the cool part, right? I just started a YouTube channel that has all the old streams, and I started because Twitch essentially kills a stream after like 9 days, and I wanted to keep some of these things alive for my reference and some of the people's reference as well. So if you go to YouTube and just search for reasonable coding, I believe you should be able to find me. Reasonable coding. I don't know. Does that work? Yes. Great. There. But I'll drop a link in the channel as well if you want to follow there. And if you like the stuff there, which should be the same thing as here, feel free to just like subscribe. Cool. Oh, for anyone that hasn't seen it, this will just look like, hasn't heard me, this will look terrible. Like the host just dropped a link to the YouTube channel. Anyway, okay, there we are. I'm actually kind of proud of how this looked. I'm not a designer myself. I tried to take to pay attention to accessibility standards, and the colors look nice there as well. But I don't know. Hopefully, if you know a good designer, maybe they can help me out with a brand or something. I don't know. We'll figure that out. Going back to resolution loops with LWT. The chaining of promised resolutions through callbacks can be seen as a kind of a dependency graph that we just saw, in which nodes are pending promises and the edges are callbacks, right? During the resolution loop, LWT starts at some initial promise that is getting resolved by the user, and recursively resolves all dependent promises. The graph is modified. Resolved promises are no longer pending, so they're no longer part of the graph. Some of these dependencies are explicit to LWT, the callbacks registered by LWT bind. Others are not visible to LWT at all, because the user can always register a callback using a function like onSuccess. Interesting. All the explicit dependencies are created by LWT's own sequential and concurrent composition functions, such as bind, join, etc. Whether dependencies are explicit or not is relevant only to cancellation. So I'm wondering what would happen, because it doesn't really say. Some of these dependencies are explicit to LWT, others are not visible to LWT. What happens when you register a callback on your own that will not be, what do you call this? Registered or visible to LWT. I had it right there. I'm gonna skip the cancellation bits. Okay. Let's skip the cancellation bit and talk about I/O. So the LWT core deliberately doesn't do I/O, which is interesting. It's it might be portable to other runtimes in that way. The resolution loop stops running once no promises can be resolved immediately. It has to be restarted later by some surrounding I/O loop. This I/O loop typically keeps track of pending promises that represent blocked or in progress I/O. Other pending promises that indirectly depend on I/O are not explicitly tracked. They are retained in memory by references captured inside callbacks. On Unix and Windows, a separate top-level loop, typically LWT main run, is necessary to repeatedly call select, epoll, or k event resolve block I/O promises. Right. So as soon as the OS is telling your OCaml program or your Reason Native program, hey, this socket you were trying to read from is good for reading, that's when LWT main gets awoken, and it will resolve your IO promise, and then that will trigger the callbacks that you have in the rest of your code to execute. In JavaScript, references to promises are retained by JavaScript code, which is in turn triggered by the JS engine. In other words, the top-level loop is buried inside the JS engine. Okay. This separation of the LWT core from the top-level IO loop keeps the core portable. All right. I hear you. Promise proxying in LWT bind, which is a function that has a signature. It takes a promise of A and goes from a function that goes from a value A to a promise B and returns a promise B, also known as flat map in other languages. The outer BT, the outer B promise, is created by bind first and return to the user. So bind really just creates a new promise immediately and returns to that. And the inner promise that's created by the user, which is the one that you create here, is returned to bind, right? And that point bind needs to make the inner and outer behave, right? So it will just proxy this one into this one. This is accomplished by making one of the promises point to the other. Right, okay, so when you resolve with whatever value was resolved from the other one, but if it was rejected, you reject and so on, I believe. This is okay, I'll just keep reading. The first of the promises this becomes a proxy, and the other is its underlying promise. After that, all operations that would be performed by LWT on the proxy are instead performed on the underlying promise. This is ensured by the numerous calls to the internal function underlying in this file. Because of the pervasive use of underlying, proxies can be more or less ignored on a first reading the code. On a first reading of the code. Let's make no, okay. We'll try to fix this in a second. However, becoming a proxy is a kind of state change, and any promise that is returned by a callback to bind or to a similar LWT function might become a proxy. That means just about any promise that is handed to the user might become a proxy promise by the next time LWT sees it. This is important for reasoning about possible state changes in implementations of LWT, and is referenced in some implementation detailed comments. Okay. Just about any promise that is handed to the user might become a proxy promise by the next time LWT sees it. Huh. Interesting. And then we have, yay. Okay. Sequence associated storage. So it has a key value map. The map can be preserved across sequential composition functions so that it has the same state in the user's callback f as it did at the time the user called LWT bind p with f. The details are pretty straightforward and discussed in the module sequence associated storage. The main thing to be aware of is the many references to current storage throughout LWT, which are needed to properly save and restore the mapping. Okay, so this is the bits that I really wanna. Yo, look at that, we're experts apparently, and I feel I don't know shit yet. Cool. All right, type system abuse. The implementation uses the type system somewhat extensively. I like that. Gentle introductions can be found here and there. Okay, let's open some of those links and see where they take us. I'm also gonna move this this code all the way to 0 there, so I can quickly access it. Does this sound familiar? Yeah. Okay, I'm not sure what format or how much information you would like, let me know, but here's a summary. I'm simplifying and omitting irrelevant details. If you want a more general and simpler discussion of GADTs, let me and the community know. Those callbacks are used to implement things like bind, join. When the state becomes resolved or failed. Therefore, those are only two possible constructors that can be passed to the callbacks. But the problem, as you can see, is that the type promise state has the third constructor pending, so LWTML was littered with code like this. Pending. Right. Case is impossible, type system doesn't know. This is a simple example, but the large number of undocumented assert faults, especially in rather esoteric helpers. Yeah. It's clear that the case shouldn't happen, but no, why not? Okay. There is a runtime error, so one is never sure if some crazy scenario can trigger it. And then the tests are thorough enough. That makes sense. Why not use result? Look at that. So they are using type state here to say that a promise, there are no values in these types, their only purpose is for the compiler to think that they are different types from each other. Perfect. So we have one over here and one over there, and this will be the value, and this will actually be the type state, the phantom type. Resolved, failed, pending. So resolved is completed, so it's failed, but pending is a completely different type. Exactly, so now when you make a match over that, you can say if I have a pending here, then essentially I will never run into failed or resolved. And if you have completed, you'll never run into pending. This is much more verbose, but the only material differences here are we tell the compiler what kind of promise state each constructor produces, instead of everything being just one kind of a promise state. Here is now a completed promise state and a pending promise state. I love how that reads. Sometimes it just reads nicely. Sometimes. We tell the compiler that callbacks take only the completed variety of promise state. Now, because the compiler knows that callbacks don't take a pending state, that's why we need that type pending to be different from completed. We can do this. Callback is a function that takes p new state and matches it with resolved and failed. and simply drop the pending case, because again the arguments p new state has type A, completed promise state in callbacks. And in the place where we call these callbacks in the implementation, the compiler does not allow us to pass a promise state that even might be pending. Great. The representation of this GADT in memory and runtime is the same as the original variant shown above, but through the type system, we know that at this point only the first two cases are possible. This is very interesting. I did not know that. And this actually solves a question I had with HTTP-GIT as well. In fact, not only can we write the callback that way, but we have to. The compiler will yell cryptic errors at us if we accidentally add a pending case. It probably wouldn't have used a GADT if this was the only thing we wanted to push into the type system. It will be overkill. If you want to see what else the GADTs are used for, take a look in the file. Hopefully, it's documented clearly enough. Otherwise, questions are welcome. Okay, I'm loving this. I think I have an account. Nope, but I definitely have logged before with GitHub. Don't look at my password. There you go. Cool. So I'm gonna save this. Yes, heart. Great. The other comment that he said was this one. Why not use polymorphic variance? Is it because of the sometimes needed coercion syntactic noise? I was planning to discuss how to handle this using polymorphic variance, also pointed out by Cristiano C. I think this is one of the guys working on GenType. So here it is. As a teaser, the syntactic noise of coercion turns out to be a good thing relative to what we actually resort to. Right, so you have two poly variants for pending and completed, and the promise state has all the constructors. There are several subtle difficulties. One is that we actually use an existential type right in the real promise state, but let's set aside for the existential type post and focus on simpler and more immediate things. Let's try writing the function that takes a pending promise and completes it. This is the existing state, so we need to handle resolved and failed. The problem here is that we can't easily write a type for a promise whose state field can only be pending. So far, we can only put constraints directly on the constructors of promise state. And the solution is to add more type information to the promise. One way to solve this is with types like completed and pending from the previous post, which we can use. We would like to link each constructor with a possible value of type variable, state, completed or pending. And that's exactly 50% of what GADTs do. The other 50% being existential types. So let's just use a GADT. GADT. So with types completed and pending and a GADT, we get to have not only pending promise states, but also pending promise. So we can write complete pending promise. Right. And this will give you a promise state that's completed. And the entire match expression reduces to a let. The magic is a source of major embarrassment. B. Need to practice the B's and the B's. Insisting on polymorphic variants. Another way to get precise typing but using polymorphic variants is to use promise state itself as a type argument to promise. Regarding the question, right. But I wonder if you could deconstruct and reconstruct that. Not sure. Polymorphic variant, if P is in a pending state promise, then it has a pending state. And we also have to use object magic to assign, right, to change the phantom type. As far as I know, this is an inevitable trade-off when you have such precise types, but also immutability. What we currently do, right, you want to change the type without actually constructing it. Okay, that makes sense now. What we currently do in LWTML is hide object magic inside a set state function. And you're supposed to do always call it like this. Set state P, some new state. Okay. This is a cheap imitation of restricted form of linear typing. In practice, P is never used in LWTML after set state anyway, but we still call set state and shadow the reference in order to be extra careful and paranoid. I want to know that all of this is purely internal to the implementation of LWT. No user has to interact with this casting nor GADTs, etc. And if you have a better way, please propose or contribute it. I already logged in. Just let me like this post. I'm gonna drink some water. Cool. What the hell do I have here? Oh my god, this is amazing. Bloody, you're bloody awesome. Bloody, I don't know how to pronounce your name. Thank you either way. Yay, this is so nice. Oh god, Antron is on fire in this thread. How ordinary variants are represented in memory. I definitely want to read this. Okay, I'm gonna leave a link open to this one in particular. I really, really want to read this post. In the meantime, let's go to the short summary to see if we can recap what we just read. The promise state is internally a generalized algebraic data type which encodes a state in its type parameters. Thus, if you do let P underline P, the shadowing reference P is statically known not to be a proxy, and the compiler knows that the corresponding match case proxy is impossible. Okay, so this essentially will be mutating the reference to P, not only changing its type, but also making sure that it actually points to the promise that the proxy was pointing to. The external promise type, AT, and the external resolver type, AU, are not GADTs. Furthermore, they are respectively covariant and contravariant in A, while the internal promise type is invariant in A. For these reasons, there are nasty casts between AT, AU, and the internal promise type. The implementation is, of course, written in terms of the internal type. Okay, look at that. I was under the impression that they would be using this for something, but they're calling it nasty. Maybe it's something they have to stick with now. That was introduced a long time ago. I don't know. We can continue. Casting from AT to an internal promise produces a reference for which the state is unknown. This is simulated with a helper GADT which encodes existential types. There are several similar casts which are used to document possible state changes between the time a promise is created and the later time it is used in a callback. You can see these casts in action in LDBT bind. The cast syntax is pretty light, and besides being commented in bind, all such casts are documented in modules, public types, and basic helpers. I don't consider myself an expert. I certainly understand a little bit more of what's going on. It looks pretty cool. If you made it this far, you are an LDBT expert. Rejoice! Yay! Yay! Can I get a hell yeah? Sorry. Oh, thanks. Hell yeah, yeah. Just blowing my nose over here. Okay. Okay, so these are the main internal types. Phantom types were used with types promise and state. These are never constructed. The purpose of the constructors is to prove to the type checker that these types are distinct from each other. Warning 37, unused constructor therefore has to be temporarily suppressed. So there's a type for underlying promises, there's a type for proxies, there's a type for resolved promises, there's a type for pending. Promise is proper, which is, I guess, the actual underlying promise type. AUC, where A seems to be the actual result. I'm gonna go with whether it's underlined or no, and C is whether it's completed or no, right? So we have the type, we have underline, underline, and then resolve. So we can use this type state all over the place to make sure that we handle different states, combinations of states of the promises. But of course, the only combinations that are possible are the ones that we see here. Note, a promise whose state is proxy is a proxy promise. A promise whose state is not proxy is an underlying promise. The underlying promise of P is P if P is itself underlying. Otherwise, P is a proxy and has state proxy P. The underlying proxy of P is the underlying proxy of P prime. All right. Another note, when a promise is resolved or becomes a proxy, its state field is mutated. This invalidates the type invariance on the promise, the internal function. For details about that, when an LRT function has a reference to a promise and also registers a callback that has a reference to the same promise, the invariance on the reference may become invalid by the time the callback is called. All such callbacks have comments explaining what the valid invariants are at the point. Okay, and cast to get the correct typing, and 2 document the potential state change for readers of the code. So we have callbacks, which is a list of regular callback, which is a function from resolve state to unit. Cancel callback, which is unit. Resolve state. Isn't this used somewhere here? No. Where is it? Thanks. I'm really just trying to learn myself, and if anyone else can learn through me learning, then that's great. But I'm actually considering branching off to other languages as well. As I said at the beginning, in the where is it? I don't know if I have it open somewhere. I've done a bunch of Erlang in the past, and I would like to touch some of it again, get back to it. So it's likely that some of those, the future live streams, if you go to events, you'll see there's at least one that I've scheduled in a few weeks to build a GraphQL server in Erlang. And I think I'd like to cover some other things. Like, for example, I'd like to do a Ponylang live stream. I have no idea how to use it. I have no idea how it works internally. I just want to bring it up, bring the tutorial, and just make a fool of myself. But, learn something on the way. And I'm sure some people will find it entertaining and valuable. If anything, it demysticizes the idea that learning a new programming language is super hard or impossible, which I think is part of what I'm trying to do here, right? We have this library LWT, and it does great work, and we don't really understand how it does it. So we just sit down and dig through it, and it might take 2 hours and 14 minutes and counting to get to an understanding of this is really the core of how it works. This is really why when I call bind and when I call map on it and when I do LWT main run, things actually happen. But the rewards that you get after going through all that are just immense. I mean, not after the library doing that, but after you understanding what it does. And if I can do it, anyone can. It's just, we all just have to sit down and try to do it, I guess. But thanks, I really appreciate the words and the encouragement. Poo. Alright, so it seems that the main module types just defines the GADT that represents the state, which is the one that we were seeing in the blog posts from the forums. And it has a type, a record of mutable lists that encodes the different callbacks. And the callback list itself, I can't seem to find yet. Yeah, here it is. It's essentially when cancel callback list is empty. These are just cancel callback, regular callback. There you go. These are just regular variants that encode all of the possible alternatives. For example, empty or concat, which means has more than one. List implicitly removed callback. I'm not entirely sure what these two mean. I guess implicitly removed callback would be a call. I'm guessing, so it's probably wrong. So I won't. But this one is removable callback, which is oh wait. Right. This is just a single one, except for the concat case. I'm just curious why they didn't make this a list instead of just make it. Instead of making their own inductive ADT for it. Might be some performance reasons, maybe, I don't know. Console callbacks behave very similarly, but they have different constructors here. And how to cancel, essentially, is another GADT. Not cancelable, how to cancel this promise, propagate cancel to one, to several. Interesting. We'll have to take a look at how these different callback types are being used in the future, in the rest of the code. Okay, so more notes. These type definitions are guilty of performing several optimizations without which they would be much easier to understand. The type parameters of resolved state guarantee that it is either fulfilled or rejected, so it is equivalent to result, and indeed should have an identical memory representation. As per the overview, there are regular callbacks and cancel callbacks. Cancel callbacks are called only on cancellation and then before any regular callbacks are called. Despite the different types for the two kinds of callbacks, they are otherwise the same. Cancel callbacks just don't need a result state argument because it is known to be rejected cancelled. That makes sense. Regular callbacks are not allowed to raise exceptions. All regular callbacks are created in this file, so this can be checked. Cancel callbacks can raise exceptions, but if they do so, the exceptions are passed to a sync exception hook. How to cancel implements the dependency graph mentioned in the overview. It is traversed backwards during cancel. It is a GADT because we don't care about the actual types of the promise references stored or their invariants. The constructors correspond to pending promise kinds as follows. No cancelable is an initial promise for wait. Cancel this promise is an initial promise for task. Propagate cancel to 1 seems to be the promise after sequential composition, and that makes sense. If you cancel A and you're sequencing A with B, then you need to cancel B too. And propagate cancel to several 1, concurrent compositions. Join. The two callback list types are ordinarily append-friendly lists with two organizations inlined. Regular callback list apparently has two kinds of regular callbacks, implicitly removed and explicitly removable. Wondering what that means. It's just that for some callbacks they will only be removed at the same time that the promise they are attached to becomes resolved. When that happens, the entire state of the promise changes to fulfilled or rejected, and the reference to the whole callback list is simply lost. forever, never to return. This removes a callback. For these callbacks, regular callback list attempts to trim an option, and a reference cell with the regular callback list implicitly removed callback constructor. Right, okay. Right, okay, that makes sense. So if it has to remove a callback, then at some point it will just take this and replace one of them with an implicitly removed callback. All right, that makes sense so far. This means that if we were to make an implementation of these promises with a very vague understanding, the initial thoughts that we had, right, of a promise being pending and resolved, clearly will not really scale through all of the complexities that something that LWT requires, but it might be enough for us to define this dependency graph. It's really a computation graph, right, that will be evaluated at some point when we resolve the first one. It sort of reminds me to the incremental or really just what was it called? I forget the name. Incremental self-adjusting computation PDF. And I hope it's this one. Akar, yes, this is the one. By Umut Akar. No, I have not read the whole of this thing, but as from the abstract, this thesis investigates a model of computation called self-adjusting computation, where computations adjust to any external changes to the data state automatically. You define a mesh of, a graph of computations and how data flows through it, and then you can only re-evaluate you may only re-evaluate the parts that have changed their inputs, which is essentially what the reconciler of React is doing, for example. Now I actually kind of want to take a look at this again. I wonder if someone printed this as a book. I'm just gonna take a look at it. Umut Akar, self-adjusting computation. Maybe Amazon has this. News one combinator. Just 17 points. Right, I forget that most of the popular things in Hacker News end up just being things people can troll on. Should probably not go there now. Anyways, I'll leave this here. We've been through this thing, we've been through this as well. Okay, we were talking about the promises that we could build. And I guess that if we wanted to have a look, implementation, complex. If we wanted to make this thing work to some degree, we probably want to, we do want to do this, right? We want to have every promise evaluate all of its callbacks, maybe after we resolve it. And Then when it's resolved, we want to do nothing, and we want to return the resolver, and then this will be our map. We'll just call it map, right? If it's pending, then we return that. We mutate this thing. I honestly don't believe that this is how the map in LWT is working. We can take a look at that in a second, but it will roughly do similar things, I believe. And then we would probably want to have something like a bind that will take an F and some promise, right? And then this thing will bind, and then this will be X, and then make. I guess we could call this like the Q. So in this bind, we get access to the value that's inside of the promise P that we made, right? I'm getting sleepy over here. Things are starting to make less sense. But essentially, we want to return this Q over there. Actually, we'll just do rest to like 20. And we want to take this value X, and we want to return Q. But we want to take Q, and we want to map Q with X. Saving. So bind should take a function that will return a promise, right? And then we need to if P is resolved, do we need to access P directly here? Wonder. So what do we need to do? Okay, so I think that here we need to always return resolved. No, wait. What? Why? Alright, so there's a few things in the type system here that don't make a lot of sense. For example, this branch seems to be unit, but this branch will be whatever f returns. And we always want to return promise, but we also want to change the type of the promise as it goes through this, right? So essentially, if we have from A to B, and we take a T of A, then we want to return a T of B. Like that's the definition of map, right? And if we write the bind, then we know that we get a T of B. So we're gonna F and P, right? Like it. Cool. So those are the types. So that means given a function and some promise of A, then we want to return a promise of B, because the function goes from A's to B's. So if the promise this is actually wrong. It's very, very wrong. Essentially, what we want to do when we map, we want to run this thing before it hits all of the callbacks, which in a way kind of means that we need to prepend or pre-compose each one of the callbacks with it. We do need to return a promise, but it might be a different promise, the one that we return. So let's say that we do, I guess we need to switch on P, and if P is pending, we will create a new promise pending. This is very likely not the way it's done in there, but we could potentially take this list of functions and just wrap them around with lambda that will pre-compose f on them, so that when they run essentially all of the maps are there. But we need a list of callback to define what the hell is a callback. So this is not actually going to work until we define what a callback is. How do they define callbacks? Regular callback list. It's some type A. And what do they use here? They don't actually define it. Yeah, they do. It's a function like this from the resolve state. And the resolve state is a state which is defined. Where is it defined? State equals, there you go. So it's one of these things. But it's only one of those that it's underlined and resolved. So if I understand what's going on here, which I think I don't, is that callbacks can only callbacks will be functions from some resolve state A to unit, where the resolve state is the underlying promise of something. So it's not a proxy promise, and it's a resolve state. And lists of these callbacks will be one of these two, right? So this empty, and this is cons, so that we can build up a list with them, right? But then these two are the actual values that have some semantic meaning, which is either an implicitly removed callback, which is a regular callback of this type, right? Or an explicitly removable, which I believe when we're building them up together, they're normally explicitly removable, and then when they're removed, they become implicitly removed. I don't know, this is just my intuition. We should probably read the code of some of these things. Okay, so after having read through the whole of the type definitions, I think that we should take a look at how bind works. Nice. So if we do let bind, a lot of the code below can probably be deduplicated in some way, especially if assuming lambda. What's immediately above? Make into proxy. Okay. So this turns it into an internal promise, and then it follows any links, any proxies that it has. So in case LWT-bind needs to defer the call to f, this function will be called to create the promise p prime prime that must be returned to the caller immediately. The callback to resolve p prime prime. LWT-bind defers the call to f in two circumstances. The promise p is pending, the promise p is fulfilled, but the current callback call nesting depth is such that the call to f must go into the callback queue in order to avoid stack overflow. Oof. Damn. I'm gonna need a break anytime now. Initially, trying to cancel the stretch pairing promise P prime will propagate the cancellation attempt to P backwards through the promise dependency graph. So I'm not sure what current storage is. So this bit I get, you want to turn it into an internal promise, and then you want to follow the proxy until you find an actual underlying promise. And when you create the new promise that propagates cancellation to the upper one, and then you save the current storage, which I don't know what it is, but you have a callback here, right? And this callback will take a look at the result, whatever that is, and if it's fulfilled, then it will take the saved storage and put it back in. So restore the saved storage essentially, and it will create a promise B prime that will try to evaluate f of b, which is the value that you fulfill the promise with. No, this is not a promise set, this is just an evaluation. And if it fails, it will go fail, which I'm not entirely sure what it would do with the exception. But I'm hoping that this will actually either hold P, yeah, and then it will turn it into an internal promise, right? Because f of b will return a promise as well, right? And fail is actually a combinator that returns a failed promise. So this is a promise, and then we turn that promise, which is the second one, the one that we're returning on our new function, right, into an internal promise. And then we turn this one into a proxy, because now we have to proxy, right, exactly, we need to proxy the other promise into this one. And now that it's a proxy, what's on my promise that I will read it above, right? And it may become a proxy by the time this code is being executed. However, it is still either an underlying pending promise or a proxy for a pending promise. Therefore, maybe now proxy produces a reference with the right type variable. We immediately get P's. Okay, perfect. So essentially, while this thing over here was originally just an underlying promise, it may have become a proxy. So that's why we're just trying to get the right reference to, so that if it is a proxy, then we just get the underlying one from it. State may have changed, making the proxy. And I guess this one is the one that joins two things together, and we ignore the proxy altogether. So this is the stitching code that they're doing between the promise that gets created when you bind something and the promise that you actually will return from the function that you're binding to the promise that you originally had. So it's a code that will make sure that this promise, right, and this promise, no, never mind. The code that will make that sure that this promise, right, and this promise inside here are stitched together properly. So the value of this one inside here actually ends up appearing outside. So if I was to do a map here and do like Z, right, like that, then this promise will get the value of this promise through the stitching promise in the middle, and thus we'll be able to map over it and access the value that in this case will be equals to 1 plus 1 is 2, and then 22. But when the promise is rejected instead of fulfilled, then we just do the same trick again to make sure that we get it, to see if it is gonna be to see if it's become a proxy now. So we access the underlying promise, and the promise that it's below it, or that it points to. So the promise that it's stitching, I guess. I think that's what it means. And then we just resolve it as with the result of rejected. And then we return two things, which is the promise, a public promise that is the originally an underlying promise that eventually becomes that may become a proxy promise, and then the callback function. Wait, is that where it ends? No, not even. Okay, so this is just a call to this create result promise and callback if deferred. And then we take the first promise. Okay, so this is where we actually take the first promise. In this case, the one on the left, right, for the first bind. And if it's fulfilled, we'll run callback or defer it, which does some things. And the callback here is just trying to run it. And if deferred, this create result promise and callback if deferred. Right, you get the promise and the callback, and then you return these three things, which I assume this function knows how to execute at some point in the future. Cool. If it's rejected, we just make it a public promise, so we completely ignore the binding. And if it's pending, we just create a promise and add implicitly removed callback. This naming is still a little bit tricky for me to follow. I need to get my head around it. But I reckon that, I mean, from the size of this implementation, we are somewhere along here on the screen, right? If you look at the cursor, and this is line, let's say 2000, so it might be 3400 or so. Mark there. Oh, just 300. Okay. 3000. Sorry, 300. So it's a fairly big library. I don't expect it to understand all of it, all of the intricacies, in just a few hours of sitting around and reading the code. But I have a better idea of what's really going on now, right? At least that leaves me much more at ease. Cool. So backtrace bind. I don't know what this is for. This doesn't ring any bells. I mean, it's similar to the other thing that we were doing before. What do we call it? Anyways, lastly, we match with the state again. Wait. No, that was it. Yeah, that was it. Yeah, this was the end of bind. This backtrace bind is, I guess, for debugging purposes. Okay, so this does a bunch of things, but roughly we will create the promise as we firstly we'll try to follow the promise on the left hand side, right? This one, to see if it's deferred or not. Our silly implementation that doesn't even type check doesn't have such a thing, so it will always just be the promise. and then after that it tries to create a result promise and the callback if it needs to be deferred. But the gist of it, right, is this one over here. If the promise is fulfilled, then you have a value, and then essentially you want to run the callback or defer it. And if you run it, then you just run it. And that would mean that if we had a bind function here, right, then we'll just have to do a switch on the P. And if this is resolved, which is our version of fulfilled, and then you have a value here, right, then you would just call this. But if it's pending, which is what you had to see here, then you would want to get the callbacks. So this is additional machinery that they need to be able to run these promises without Stack Overflowing, as I understand it. If it's rejected, then we just return a public promise that has this result as its current state. But we don't have a rejected state in our pinky promise because it will never be rejected. It's just pending, and then at some point it is resolved. That's what a pinky promise is, right? But when it's pending, what this is doing is essentially adding to the list of callbacks the function that we have. So this will return a pending promise, nay. This will actually mutate P by saying F will be one of the callbacks that you need to call, and then you will return P. And that makes more sense to me. And I reckon that we should be able to implement map on top bind. So bind essentially is our sequencing function that we might as well just define as P of F, and then this is bind F and P. So now you can do this. And this looks very monadic. Ooh, so monad. Actually, let's just do a very simple example and let's try to get it to compile. I'm gonna close this thing over here. And I'm gonna do I'm just gonna make a Dune file, executable, name, picky promise, and it has no dependencies. So Dune build. What? No way. I didn't know that Dune build created the file automatically. This build nothing. Okay, interesting. Cool. And our callback essentially was we will need a type for state, and this we can just say it's A, and it's a result of A. Huh. I guess we can just remove this thing and just say there would be a name. And if you want to pass it so let's just make these promises work like this. Ideally, we'll be able to generalize this to any state, but right now I don't have the energy to go through all that. I just want to get something up and running, and then we can see what happens when we generalize it later. Okay, so now that we know that this is T of int, which means this will be an int, which means this is a function there. Okay, now things seem to be type checking. Nice. It'd be nice if this was not like that. So maybe, just maybe, we can make this be okay, let's just do a GADT here. So empty, and then this would be like input and output, and then callback y and o. Actually, we probably want to just ignore these parameters here, and then we want to say cons, and then if you give me a function from input to output, and then you give me a callback from, wait, do I need that? No, I don't. Do I? Maybe I need to execute it. Yeah, I think I'll need to recover the data types. And you give me a callback from some A to some B. Then I'll give you a callback from I to O. No, I'm too lazy to do GADTs right now. Did I say lazy? So I think this makes a little more sense. Build, cool. So no magic variance anywhere. Yeah, and line 11, we have a problem. How do you know this is an int? How could you possibly know that? Build again. Line 11, still bind has a signature. Once you solve, you get a B. And that's a B, and then you call that, and you get a T of B. And that makes sense. These are just the promises that we're making here. So what's the problem? Expression has type A to unit of list. Why is it results? Where is it that we do a result? Oh, we do okay somewhere. There you go. Cool. So line 20. That's a ref of TB. Right. So our T actually will have a promise inside. So mutable P, promise of A. So so this is a TB. That's a TB, but otherwise, why? So for the pending case, we actually want to make a new promise. I am not sure. I get that we will need to return a P that right now is really it's a it's a T of A regardless of what it says there. Right, if I remove that, then this is T of A. So there will, at some point we'll have to do some magic crap. Probably we can do some better things than object magic here, but for the time being, this will make this change. Now the reality is that we want to make a new promise, right? That will have this type, and we want to do that by I wonder if we do need to modify the callbacks at all. So if the original promise is pending, so if this one is pending, right, then this should just be added to the list of callbacks, so that when this resolves, then we call this thing, right? However, the promise that we return needs to be a promise that has the type that's returned by this function over here. So we can't just modify the we can't just modify the list of subscribers. And putting the subscriber there also wouldn't quite work. Why? Because subscribers have type some type to unit, and f clearly does not behave like that. F returns another promise. So if we call f so this will be some a, and if we call okay, I think I have it. So we will need to essentially make a new promise, right? And then we get our resolver, and then we can make a new function that will get some a. I'm just calling it a in there, and this is something that f of a can actually take, right? And we will return that promise, and that promise should essentially look something like this. And resolve has TB of unit, perfect. So resolve takes a TB, and f takes an a and returns a TB, so this should be a unit. Great. Which means, if I'm not mistaken, some of these things should just type check. Except line 21 continues to expect something different. What the hell are you expecting? So P is a TA and state is a reference to A. I don't seem to quite be getting this. Line 22. We extract the state from the reference. We know that if it's resolved, we just call the f function and we return the next function, the next promise. But if it's pending, we want to make a wrapping promise, so we create a new promise that will eventually resolve when the callback to this one gets called, and that I understand. So we add this new f prime to the list of callbacks of p, and then we return p prime, and then this callback will eventually be called, and we will call res, which is the function that comes from in there, I wonder if the problem is that P then becomes a okay. Shouldn't... Right. So you should be a state, like that. So this should be a T, perfect. Result takes some A, and then it gets a state of the promise, and puts the callbacks in the right place, and if it's resolved, it does nothing. And returns a T and a A unit. Good. So line 8, what are you complaining about? Line 29. Precisely. So here we want to do a switch. Right. Okay. That worked. Awesome. Okay. Ooh, I'm actually surprised that this even did something. Okay, so I mean, sure, it's not the most beautiful of promise libraries out there, but Pinky Promise seems to be working. Seems to be actually putting some functions in there and essentially sequencing function calls and handling promises that are resolved and not resolved. So I wonder if what will happen if we just resolve the 2 first. Cool. And then it doesn't matter the resolution order, things will always be there. So essentially we ended up having a promise type that represents a pending promise with a list of callbacks, or a result promise with a value, and a type for this promise really that includes a state that's mutable of the promise. And we can make a promise new by calling make, and we get the promise back, but we also get the resolution function we can call to resolve it. And this is just going to mutate some state internally, and if the promise goes from pending to resolve, it's just going to execute the list of callbacks at the point of resolving this function. And we have a basic bind that essentially will take a function that will generate a new promise and one promise, and it will read into the first promise, and if it's resolved, it just returns the result of the second of the function, which will be the second promise. But if it's still pending, it will create a third promise that will act as our proxy promise that we will immediately return, and it will create a function that will be a new callback to the first promise that we passed in, right? So we add this new function into the callbacks of P, the first promise, because it's still pending, so that when P resolves, then this function gets called. And this function just executes F, which is the function that we want to bind P to. And the new promise that comes out of that can either be resolved or can essentially still be pending. If it's still pending, then we just we'll tell it to at some point when it resolves, execute the resolution function from the third promise that we had created in line 25 that we return in line 34. But if it's already resolved, as in line 29, then we would just call this resolution function directly so that it immediately continues the chain. And it is my belief that we should be able to, if we make a helper function here, let's say let return, right? That takes a value and it will just return you a result promise here, or return we can do return. We can just do something like this. There will be a promise, and we return the promise, and we just resolve X. Of course, we could also just construct this promise as a state ref resolved X, right? So it would be closer to the internal representation. So now here, instead of doing this magic, we can just say return whatever unit. We build again, we execute, still runs the same, and we can add some more sugar here. So essentially, if we do this, then we should be able to sequence in the same way. But now this looks a little nicer. Oops, sorry. No, that's not quite. So P binding will give us an X, which we can use for doing things. And then if we want to use X inside of with Q, then we need to essentially bind inside like we had before. Cool. Of course, this is not actually doing any I'm curious, would you actually call this a concurrent library? I don't think I would. To me, it's just interleaving the execution of, and as I said, of course it sounds very concurrent, but it's just interleaving the execution of callbacks. And no, wait, not even that. No, that's utter bullshit. What this is doing is simply executing a computation graph. So you begin at the top level node, and then you go through all the callbacks and so on. And bind just is a way of attaching yourself to this computation graph at some point. We'll just remove those over there, and let's add a new, more higher level primitive, sorry, not primitive, but a utility. Let's call wait. And this will take a time, t, right? And it will return, it will do two things. It will return a promise immediately. So but it will resolve this promise some point in the future. Now, how do we do that? I think that's the key here, right? How do we define a function like LUT async? And I think this one is actually, this is one of the functions that actually provides the synchronicity. Okay, so if we get something like async working, then I'll be very happy. Right, but we'll never be able to get through a synchronicity here unless this is not a blocking call and it's something that's implemented in terms of the underlying async IO that the operating system provides. Interesting. So of course, if if we do this, this will make sense. I mean, it will work. And it did. Right, because he has to return a wait. Just gonna pass along the value. Gonna pass along the value. Okay, running now. I expect to see 1, and then 2 seconds, and then 20. Okay. At least this works. But of course this is blocking code. I guess that for implementing asynchronicity we'll have to drop down lower than this. Normally the times I've seen async being used wait, let me see this. Okay. The times I've seen async being used has been with operations that were actually oh hey, this is a ReasonML. Is a syntax over OCaml that adds a few things that are more familiar for Algol or C or JavaScript like languages, such as open braces and semicolons every fucking where. But if you look closely, if you squint a little through the braces, you'll find out that you still have your types and your variance and your type parameters, and you have records and the whole shebang. And the pattern matching with match is called switch here, which is essentially the same thing. Like if this was OCaml, this would be match with, and then the value here, and the fat arrows will be thin arrows. But other than that, it's potato tomato sort of situation. It uses the same toolchain for native, and it uses the BackScript compiler for. Oh, sorry. My bad. So you will likely not have any of these things in C++. These are algebraic data types. It's a way of defining what your data looks like in terms of collections of it. For example, this promise can be pending or resolved. So it's one or the other, kind of like an enum, but you can have arbitrary data associated with it. And this one over here is a record, which means you need to have all of these things together, kind of like a struct. The type system, however, is fairly powerful compared to languages like C++, in its own way, right? Okay, so let's keep looking into Unix here, and let's see what the hell this I think was IO. What I'm looking for, server, right, this one. Establish server with client socket. Cool, let's go back to the implementation file and take a look at what it has inside. No, actually, I'm a dropout. I was doing software engineering back in Argentina, and I just didn't like the the contents, the pressure to learn that the teachers did not put on us, and just the overall, the overall approach that university had. So I figured, well, if I'm not enjoying myself here, I might as well do something else. And but I've been coding for some time. Sometime now. I had already been coding for some time professionally before I dropped out. If anything, I think that most of the things I've learned that are useful at work right now have been things I've learned outside of university. Reading a crap ton of books, going through RFCs from the internet, such as what the protocols are, TCP, IP, DNS, and so on, and the white papers, which is a little bit of, hey, this is academia, right? But I don't know, where I was studying, they did not encourage you to pursue knowledge in that way. You know what I mean? They were like, hey, this is what we need for the local industry. But I come from a very small town in Argentina, so it kind of makes sense in that context. I don't blame anyone for it. It just wasn't for me. So clearly the one that's doing the heavy lifting here is bind. So if we go into LWT Unix, where is it? Here, and we go into bind. I guess let's bind. Check file descriptor. Right, precisely. Okay, so this one over here is the one that just returns immediately by just setting up a file descriptor. It is not, I repeat, it is not actually waiting for anything to happen. It is not doing any magic whatsoever. If we have a Unix address, it will just try to find a job and run it. Bind to a job, and bind job is just an external call. And run job is somewhere here. I can find it here. Yeah, which boils down to an external call. Okay. So I guess in these tabs over here, I'll find those calls as well. Run job should be here, and it is. Cool. Get it. Gotcha. So that's how low things have to get for you to actually get this asynchronicity. You essentially need to go to an FFI and return control immediately to your code by saying, oh, there is a promise somewhere here. And then something happens on a promise, on a process somewhere else. And then when we actually get that socket back up and running, then we'll get back to us. So I have no hopes of getting proper asynchronicity happening here. Oh well, it's still nice that we are able to do that, since we have encapsulated the sequencing inside of this monad. Essentially, whatever picks this monad up should be able to. I mean, if the result, where is it? If the resolver function didn't work so directly, then maybe we could make this be picked up by a runtime that will take one of the take one of these monads and just no, actually it doesn't make sense. As if you don't have any external inputs to a running system that provide this asynchronicity, this I'm gonna wait until something happens and then I will wake up and do something, which is happening with the asynchronous I/O mechanism that the OS provides, which for LWT Unix will be Unix, and for Windows would be Windows and the Windows APIs and so on, like select or epoll or KQ, I think. Yeah. I can't seem to think of a way of doing it. So here it will just be calling rest, resolve the top level promise, and then every other promise will resolve eventually throughout. Or, you will have to resolve all the promises at some point, but they will not resolve by themselves. But the nice thing about having this as a monad is that we could potentially change the implementation of this as long as we preserve the interface, right? And then provide a backend for Unix and Windows and so on, exactly like the way that it's being done in LWT, which is very interesting. Ooh, there's a bunch of C code here. Socket, read job. I guess Unix has similar things. Yeah. And a bunch more. But okay, I think I finally sort of understand how the asynchronicity of LWT is happening. Sure, there's a lot of things that are not entirely clear yet, but they will happen at some point. In short, from just being able to use it and having an overall idea of how the framework works, I went down to understanding the promises are data, that the way that we chain promises together by binding things together forms a computation graph that will be evaluated at some point, that every time we give this whole data structure to the event loop, the main loop, it will wait for some external I/O to happen, and if it needs to, and if there is something going on there, then it will wake up and it will evaluate. It will evaluate all of the callbacks for that particular promise, and as in turn, each one of the callbacks might actually set up different promises that have separate I/O that needs to run, and once that I/O is completed, then the runtime will again go back to each one of those promises and resolve them, and the loop repeats. The callbacks for those promises will now trigger, and so on and so forth, which is interesting. At some point, the control flow will return to LWT main run, and the event loop, will be finished. Will finish. We learned a lot about the types that they're using internally, how they're using the GADTs extensively to make it impossible to pass in. To have to resolve certain. To make it impossible to handle different possible promise states in different pieces of code. For example, some pieces of code require you to have a promise that is the underlying promise and not a proxy, and that also is resolved. So a promise that is not resolved or a promise that is a proxy will just not cut it for that piece of code. So the GADTs are helping them very, very narrowly or strictly type down what they want and what they need. There's a few blog posts if you want to read them, which I'm going to put here again. One of them, this is the main one, LWT core refactor and documented to be contributor friendly, which begins with, this brilliant post by Anton Bachin. Honestly, dude, you're doing an amazing. If you get to hear this, please, here's my thank you. The writings and all the work that you've been doing for this library seems just top notch. I'm loving it, at least. And that's not to say that people before you didn't do it. Of course, you're building on top of the shoulders of giants. So thank you, everybody who's working on LWT. And with that understanding, we've gone off to try to implement a promise library ourselves, which is a fairly small one. And it essentially models promises as pending or resolved, and it's called pinky promise because everybody knows pinky promises cannot be broken. And I translate that to they can't be rejected or cancelled. And to do this, we'll have to do some. We've learned a little bit from how they've been doing things in LWT, and we've modeled things much more minimally. But we have a creation function that will create a new promise that will also give us a resolver function that we can call at some point that will execute all of the callbacks of this promise. And then we have a binding function which acts as essentially a monadic operation to sequence different promises together. And this one was the tricky part where we had to figure out that we actually need an intermediary promise to be able to sequence the values between two of them. But once we had those two up and running, we could create promises and we can pretty much do whatever we want with them on bind. So we were able to run some examples and make another, like a sample combinator called wait that will take some time and wait for before it passes some value through. And then we printed some things, which was cool. All right, I'm actually just gonna write git ignore here. We don't need build, we don't need Merlin, we don't need install. All right, if I do that, if you want to see the code of this thing, I'm actually initial commit. I'm gonna create a new repo right now. Actually, it's just new. What is this? There you go. And we'll call this Pinky Promise and a silly little promise library. Unbreakable promise says library. Do we have an emoji that we can use for Pinky Promise here? If I search for Pinky Promise hand. Let's see if any of these hands is resembling. Like that. No, we have a. I guess we could use the cross fingers. Oh. Great. And we're gonna push the code there. I'm gonna move LWT to readme. Let's modify that. Pinky Promise. A silly little unbreakable promises library for reason built during reasonable coding. I'm gonna put the name of the channel here. Where is it? Oh, there you go. By the way, if you like this stream and you want to see some more that are no longer in Twitch, because Twitch removes the old ones, you can just go to YouTube and search for reasonable coding and you'll find a bunch of them. Some of them are very long and slow, so you can watch them in like 2x and maybe just look at some of the things that are going on. But I'm gonna start to play around with making videos rather than streams for YouTube. Yeah, and if you like anything that you see there, just like and subscribe. Will be very much appreciated. So a silly little unbreakable promises library for Reason built during a reasonable coding live stream. During the stream, we spent around 4 hours looking into LUT and its code base and documentation, trying to understand how is it that it works internally. The learnings, key learnings, are outlined below. One, promises data. Two, the event loop literally waits for some IO to happen before resolving a promise. The top level promise. Three, a promise that is resolved will call all of its callbacks with its result value, with its resolution value. Those callbacks may in turn make the event loop wait for some IO to happen before continuing. Make ask the event loop to perform some IO and wake them up when it's done, it's completed. So rough notes during the stream, or rather just stream notes. With this information, we set out to build a tiny library, a tiny promises library that could more or less be used to the same result. We found, however, that to provide actual asynchronicity, the underlying platform, runtime, or platform, needs to have some async primitives, such as promises in a JavaScript engine, or async IO at the operating system level. I'm going to put a disclaimer here. Disclaimer, some of this might be horribly wrong. Please correct me if it is. thus pinky promise remains tiny monad to sequence computations that will run sequentially. Cool. And of course we need to add the remote, which should be, where is it? Here. Cool. Right. So the repo is out there if you want to take a look at it. The code is just one file. The build config is just one file. You should build just fine in any Linux or Mac OS environment. And yeah, thank you so much for bearing with me while I learn. Thank you for learning with me. Hope you're starting a great 2019. And before we leave, I wanted to say again, take a look at some of the events in case that you want. Oh, sorry, Mr. Plus, I did not see your message. In case you're still there, take a look at some of the events, and if you like them, then subscribe and set a reminder so that you don't forget, and we'll see each other again. And if you want to take a look at some of the past events, things that have happened before that are no longer available in Twitch, do not hesitate to go to YouTube and search for it. Subscribe to the channel as well. Comment at any point if you think something should be clearer or could be cleared up, and hopefully we will make something cool out of this. Thanks Alo Darius for the follow. And okay, we have a question by Mr. Plus. How many languages do you know? I don't know. I'm fairly comfortable with quite a few, but it's I tend to jump around code a lot. I know some people don't like it. I get a little bit restless when I do just one language for a long time. If there is one language that I dread using is Java, but it pays the bills. Or JavaScript as well. But I think it's less about the languages and more about the patterns and concepts that are being applied to language design, such as type systems or enabling syntax extensions, or having a language that is pure or impure, and whether you support mutability or immutability by default, and these sort of things. If you want to be blown away, I hands down will recommend you to have a look at Erlang. It will look like a very silly thing to start learning when you're looking at C++ and everything is super fast and just like really close to the machine. But if it gives you an idea of what it's like to build systems in a really large scale, since really the primitives in Erlang are not built for making tiny programs. They're built for making massive systems that need to be alive like 99.9999% of the time. There's even a company called 99s that does Erlang software development, because they claim they actually have achieved 9/9 of uptime due to Erlang. And if you need a big company that uses it, you can say WhatsApp uses Erlang with about, 35 or 40 engineers some years ago. They power, I don't know, millions, if not billions of messages daily. Anyways, thank you so much for your time. This has been a Reasonable Coding, and I hope you liked it. Tell your friends about it, learn some reason, and as always, stay reasonable. See you around.